It happens to, like, all of us. You ask an AI to research a complex topic for you. Maybe you are prepping for a massive project. Or you're just trying to wrap your head around a completely new scientific field that you need to understand by tomorrow morning.
Right, the classic midnight cram session.
Exactly. So you type in your prompt, and the AI spits back this incredibly confident, highly readable, brilliantly formatted answer. But then you start actually poking at it.
And that is usually when the illusion breaks.
Yeah, you try to verify a claim, and you realize something kind of horrifying. It's mostly just regurgitating high-level summaries. Like, it missed the dense charts completely. It ignored the underlying math.
Yep.
And the actual rigorous evidence that proves the point is just, well, glossed over in favor of a smooth-sounding paragraph.
It gives you the illusion of depth while completely skimming the surface. I mean, the system essentially reads the back cover and the abstract and then pretends it read the entire textbook.
Right, and for casual browsing, fine.
Right.
If I want a recipe, that works. But if you actually need to rely on that information to make decisions or, drive innovation, it is a catastrophic problem.
It really is.
So welcome to today's deep dive. We are looking at a fascinating new research paper titled Agents-K1 towards agent-native knowledge orchestration. This comes to us from a massive collaboration of researchers at the Shanghai Artificial Intelligence Laboratory, East China Normal University, and Fudan University.
It's a powerhouse team.
Truly. And our mission today is to look at how this team is completely rewiring how AI systems read, understand, and connect millions of scientific papers. They're basically trying to take the AI from a casual, confident skimmer into a rigorous, fully fledged research scientist.
Which is a huge leap.
It is. Okay, let's unpack this. To appreciate how they are fixing this, we first have to look at why our current AI researchers are failing so spectacularly at reading comprehension.
Yeah, so we need to examine the massive gap between what we call agent orchestration and knowledge orchestration.
Okay, break that down for me.
Sure. Over the last couple of years, the industry has poured billions into agent orchestration. That's the part of the AI that decides how to plan tasks, write code, or, decide when to open a web browser.
The planning part.
Right. We have systems now that can plan out an entire simulated scientific experiment step by step. But the knowledge orchestration, the way the AI actually organizes, stores, and retrieves the deep knowledge it needs to perform those planned tasks, has been completely left behind in the dust.
So the AI has gotten incredibly good at writing out a detailed to-do list, but when it actually walks over to the filing cabinet to pull the files and do the work, the cabinet is just like a giant pile of shredded paper.
That is a brutally accurate analogy, yeah.
Mm-hmm.
Current systems usually rely on graph-augmented retrieval. You might have heard of frameworks like LiteRag or Raptor.
Yeah, I've seen those mentioned around.
So they take documents and build knowledge graphs out of them to help the AI search. But their critical flaw is that they rely on flat text-only triples.
Flat, meaning what exactly?
Well, they process a scientific paper by literally stripping out the complex equations, mostly because they just don't know how to format them.
Oh, wow.
Yeah, and they'll take a highly detailed, crucial table of experimental results and just reduce it to whatever the tiny caption says underneath it. They completely obliterate the deeper narrative structure of the paper.
They are essentially turning a complex three-dimensional building into a two-dimensional floor plan and throwing away all the actual load-bearing walls.
Exactly. And honestly, the worst casualty of this process is how they handle citations.
How so?
Current systems use flat citation edges. The system logs that paper A cited paper B, and that is all the information it retains.
Wait, really? Just a simple link?
Just a link. It has no idea why that citation happened. It doesn't know if paper A cited paper B to say, this is the foundational baseline of our entire field, or if it cited it to say, this previous paper is completely fraudulent, their methodology was terrible, and we are here to debunk it.
Oh, wow. Without that context, an AI might pull a debunked theory and present it as fact just because it saw a line connecting the two papers.
Happens all the time.
It sounds like current AI is acting like a lazy undergrad. The type just reading the abstracts, padding the bibliography to bulk up the word count, but completely skipping the actual charts and the dense methodology sections where the actual science happens.
Spot on.
But wait, I have to push back here. Aren't modern LLMs reading the PDFs directly now? Like, you can just upload a giant PDF and have the AI read the whole raw document.
I mean, advanced models absolutely can read raw PDFs at runtime, but consider the monumental inefficiency of that workflow.
Okay, inefficiency how?
Well, if you give an AI a complex, multi-hop question that requires synthesizing data from 20 different papers, and it has to extract the data from those raw PDFs from scratch every single time you ask a question.
Oh, I see.
Yeah, it is incredibly slow and computationally expensive. But more importantly, doing on-the-fly extraction means the way the AI reads the document might change slightly every single time based on your prompt.
Because it doesn't have a stable baseline.
Right. It's not building a permanent, reliable, structured archive. It makes it nearly impossible to trace an answer back to exact, stable evidence.
Because it's starting from zero every time, it can hallucinate different interpretations of the same PDF depending on its mood.
Exactly.
So reading raw text on the fly just isn't cutting it for true, rigorous research. We need a permanently organized archive, which means we have to fundamentally reorganize a document before the AI even tries to reason with it. So how is the Agents-K1 team actually breaking these papers down?
Well, their solution starts with a multimodal parser powered by a tool called MinerU. Instead of just grabbing the plain text and throwing the rest in the trash, it runs the document through a 5-module extraction schema.
A 5-module schema, okay.
Yeah, it doesn't just read the paper. It dissects it like a biologist dissecting a specimen. First, it pulls verifiable metadata, authors, journal, publication date, all the standard library tracking stuff. Second, it extracts explicitly mentioned concepts. These are the tangible things. The specific laboratory methods used, the performance metrics, the exact data sets they trained on.
Okay, metadata and explicit concepts make sense. That's the easy stuff. What are the other 3 modules?
Third is where it gets highly sophisticated. It extracts implicit abstractions.
Implicit abstraction. So it's not just looking for keywords. It's actually trying to read between the lines. How does a machine do that?
It's pretty clever. Let's use a hypothetical medical paper as an example. Say we have a paper testing a new chemotherapy drug.
Sure.
The explicit concepts are easy: drug X, mice, T cells. But the implicit abstraction module is looking for the motivation and the claims.
Ah, the why.
Exactly. It reads the introduction and synthesizes a structured data point that basically says, current treatments for this specific tumor cause severe liver damage, so the motivation is to test if drug X can bypass the liver entirely. It identifies the core problem and the proposed solution as structured facts, not just free-flowing text.
That is wild. It's capturing the actual narrative purpose of the research.
Yeah. And moving on to the 4th module, it maps out inter-entity relations, basically how drug X interacts specifically with those T cells. And finally, the 5th module extracts the citation intent.
Ooh! This solves the flat citation problem we discussed earlier.
Completely solves it.
Right, because now it's logging the why.
The researchers actually designed the system to grade citations on 5 distinct levels of importance.
5 levels.
Yeah, level 1 is a peripheral cite, which is maybe just a passing mention in the introduction. Level 2 is contextual. Level 3 is moderate. Level 4 is strong. And level 5 is a foundational cite, meaning the entire methodology of this new paper is fundamentally built on top of the cited work.
That creates an actual hierarchy of importance. Like, if I'm an AI trying to learn a new field, I don't want to read the level 1 passing mentions. I want to follow the level 5 foundational links straight to the core of the discipline.
Exactly. It gives the AI a roadmap.
But here's where it gets really interesting. How does the system actually link a complex math equation to a paragraph of text without getting confused? Because an equation isn't text. A bar chart definitely isn't text. How do you put them in the exact same knowledge graph?
This brings us to what the researchers call semantic anchors. And honestly, this is arguably the most elegant engineering in the entire Agents-K1 design.
Semantic anchors.
Yeah. Usually when AI systems try to process a document, they either try to force a chart and a paragraph into the exact same text format, which ruins the data, or they keep them completely separate in different databases, which means the AI can never connect them.
Right. Siloed information.
Exactly.
Yeah.
Semantic anchors create an intermediate abstraction layer. It basically acts as a modality-agnostic bridge.
Modality agnostic, meaning it doesn't care if it's looking at text, a picture, or a string of calculus.
Right. Think of a semantic anchor as a digital pin on a bulletin board. Imagine you have a complex table showing the results of our hypothetical drug X trial, and on the next page you have a paragraph discussing those results.
Okay, I'm picturing it.
The semantic anchor sits in the middle of the knowledge graph. It holds the canonical entities, the specific name of the drug, the dosage amounts, and it casts strings out to connect them. One string connects to the visual figure of the table, preserving its grid structure. Another string connects to the text paragraph.
So it's essentially a translation hub, The table speaks table, the text speaks text, and the semantic anchor translates both of them into a universal meaning so the AI can understand how they relate to each other without destroying the original format.
You've got it. It anchors the high-level scientific concept to the specific multimodal evidence. So later, when the AI makes a confident claim to you about drug X, it isn't just guessing based on a summary.
It can actually show its work.
Yes. It points right back through that anchor to the exact cell in the visual table or the exact variable in the math equation.
Okay, so we have this beautiful, perfectly structured, 5-module web of data held together by semantic anchors. But creating that level of structure usually requires massive computational power. When I first read this paper, I fully expected the engine behind this extraction process to be some massive, power-hungry supercomputer model. But the extraction backbone, the AI actually doing the reading and categorizing, is only a 4 billion parameter model.
Yeah, it's tiny.
How on earth is a model that small doing such heavy lifting across millions of dense scientific papers?
It is surprisingly small. Just to put that in context, some of the most popular commercial language models you interact with daily are hundreds of billions, sometimes over 1 trillion parameters.
Right.
A 4 billion parameter model can run on standard consumer hardware, but it punches way above its weight class because of a very specific training secret. It uses group relative policy optimization, or GRPO, combined with a strict rule-based reward system.
Group relative policy optimization. Okay, policy sounds like a set of rules, and relative sounds like a comparison. Are they pitting different AI attempts against each other with a strict rulebook to see which one follows the rules best?
You nailed the core concept. Instead of just showing the AI examples of good extraction, they use reinforcement learning.
Okay.
They give this tiny 4B model a task, like extracting all the data set names from a dense physics paper, and let it try multiple different ways to do it. Then the system grades those attempts relative to each other.
I see.
But the reward system jointly supervises 3 specific things: format compliance, JSON validity, and the actual accuracy of the extraction, what we call task-conditioned F1 scores for named entity recognition and relation extraction.
Whoa, time out. You just threw a massive handful of technical jargon at me.
Sorry about that.
No, it's good, but let's break it down. JSON validity, I get that's the coding format, and if you miss a single comma, the code breaks.
No?
But F1 scores, named entity recognition. Break that down for me like I'm a smart middle schooler, because my eyes just glazed over.
Fair enough. Let's untangle that. Named entity recognition, or NER, is just teaching the AI to spot specific important nouns.
Okay, important nouns.
Yeah, instead of just reading a sentence, it recognizes, drug X is a pharmaceutical and liver damage is a biological symptom. It's extracting the key players from the text.
Okay, spotting the important nouns makes sense. And the F1 score.
An F1 score is simply a metric for measuring accuracy that balances 2 things: precision and recall. Precision and recall, right. Precision asks, of all the things the AI highlighted as important nouns, how many were actually correct? Recall asks, out of all the important nouns buried in the paper, how many did the AI successfully find?
Oh, that makes total sense.
Yeah, the F1 score combines those to give you a single grade for how perfectly the AI extracted the information.
Got it. So the reward system is brutally strict. It's grading the AI on finding the right nouns, connecting them correctly, and organizing them into perfectly valid JSON code.
Exactly.
Because this model isn't writing poetry for a human to read. It's generating structured data for another AI to use. If the formatting is sloppy, the whole pipeline crashes.
Exactly. And by strictly rewarding the model, not just for being right, but for organizing its right answers perfectly, they managed to make this tiny 4B model incredibly hyper-efficient.
Wow.
The results in the paper show that this 4B model outperforms an 8B open source reference model across 10 different benchmarks. It actually matches a massive 32B model specifically on that named entity recognition task we just talked about.
That's incredible.
And it does all that while being vastly cheaper to run and infinitely easier to retrain when you need to introduce it to a new scientific domain.
It's like having a highly trained, specialized clerk who only knows how to file complex paperwork flawlessly, rather than hiring a brilliant generalist who knows a little bit about everything but leaves their files in a messy pile on the floor.
That's a great way to think about it. And once all that perfectly formatted data is extracted and anchored, the AI researcher needs a way to actually interact with it. So the researchers built what they call the Graph Anything CLI layer.
Okay, CLI stands for Command Line Interface.
Right, this is a tri-source interface.
A tri-source interface. Walk me through how an AI actually uses that in practice. If it's pulling from 3 different places, what does that look like?
Let's follow the AI's thought process.
Yeah.
Imagine you ask it to investigate a rare cellular reaction. First, it uses real-time web search, that's source 1, to grab the most current definition of the cell from a live database.
That's what.
Then, it uses multimodal graph retrieval source 2 to dive into the Scholar KG we built. It finds a semantic anchor linking a paragraph to a microscopic image of that exact cellular reaction.
So it's looking at the live web, and it's looking at the specific image and text in the database. What's the third source?
Cross-document network traversal.
Okay, meaning?
The AI looks at that semantic anchor, sees a level 5 foundational citation attached to it, and actively walks the graph to jump to an entirely different paper from 10 years ago, maybe a chemistry paper, that explains the foundational mechanism of why the cell reacts that way.
Oh, wow.
It seamlessly merges live search, multimodal evidence, and cross-document navigation into one smooth action.
So what does this all mean for you, the listener? If you're using an AI to map out a corporate strategy or research a new medical field or understand a complex legal landscape, with a framework like this, the AI is no longer just guessing based on fragmented text it scanned on the fly.
Exactly.
It's using a command line interface to actively query a rigorously mapped web of facts. It's exactly how a human researcher would pull files, check the footnotes, walk down the hall to the archives, and verify the original charts. It fundamentally changes the level of trust you can have in the system.
Trust and traceability are the ultimate goals here, because every single piece of information retrieved through that tri-source interface can be traced back to its specific source document, its specific paragraph, and its specific chart.
We've got the engine, we've got the interface, but a system like this is only as good as the knowledge it has access to. How much data has this team actually fed into this architecture to prove it works in the real world?
They didn't just write a theoretical paper, they unleashed it. They created what they call Scholar KG. Yeah, the team processed an astonishing 2.46 million scientific papers. And they didn't limit it to one narrow field to pad their stats. They covered 6 major disciplines: computer science, chemistry, biology, earth science, physics, and materials.
Over 2 million papers processed into this deeply interconnected multimodal graph. Just visualizing the scale of those semantic anchors linking millions of charts to millions of paragraphs across different scientific disciplines is mind-boggling.
It is a staggering achievement, and they are releasing a 1 million paper subset of this graph to the public for community research, which is honestly a massive gift to the open source community.
That's huge.
And the architecture itself is also schema adaptive. They call this potential general KG.
Meaning the pipeline isn't restricted to science. Like, you could theoretically point this 4B model at 1 million complex legal contracts, or 1 million historical primary sources, or a decade of corporate financial disclosures, and it would build the exact same kind of rigorous relational graph.
Precise.
But let's look at the hard numbers. Did giving the AI this massive, perfectly organized filing cabinet actually make it smarter?
The performance leaps they recorded on their benchmarks are jaw-dropping. They evaluated the system on the Frontier Science Research benchmark. This tests an AI's ability to answer incredibly complex, multi-hop scientific questions that require deep reasoning.
Okay.
When they took Gemini 3, a very capable language model, and forced it to rely only on standard flat retrieval, its overall accuracy was just 7.9%.
7.9%. At that point, the AI is basically just guessing blindly.
Pretty much. But when they plug that exact same Gemini 3 model into the Agents-K1 knowledge orchestration pipeline, allowing it to use that tri-source interface and the Scholar KG graph, its accuracy jumped to 24.6%.
That is a massive leap for the exact same model. Did other models see the same boost?
Across the board, GPT 5.2 went from a baseline of 25.2% accuracy up to 39.4%.
Wow.
But perhaps the most telling metric was on geoscience research questions. They measured what's called rationale accuracy.
Rationale accuracy.
Yeah, this doesn't just test if the AI randomly guessed the final multiple choice answer correctly. It tests if the logical step-by-step reasoning it took to arrive at that answer was scientifically sound. Gemini 3's rationale accuracy jumped from 52.3% to 69.5%.
So what does this all mean? To me, this completely shifts the paradigm of how we develop AI. For the last few years, everyone has been entirely focused on making the brain of the AI bigger and better. Trillions of parameters, massive server farms, building a smarter and smarter LLM.
Right.
But these numbers proved that the brain wasn't the only bottleneck. The way we were feeding it information was deeply fundamentally flawed. by providing traceable, multimodal, and relationally aware data. By giving the AI a proper filing cabinet, the exact same AI suddenly becomes exponentially smarter and more reliable.
This raises a critical point about resource allocation in AI development. We've spent billions scaling up the reasoning engines themselves. Agents-K1 proves that if you structure the knowledge environment correctly, you can unlock latent reasoning capabilities in these models that we didn't even know were there.
Yeah.
Gemini didn't suddenly learn more about geoscience overnight. It was finally given the tools to properly investigate the geoscience data that was sitting right in front of it.
It's the difference between asking a brilliant detective to solve a murder in the pitch dark versus just turning on the lights so they can see the evidence board.
Great way to put it.
Okay, we've covered a ton of ground today. Let's summarize the core journey of this deep dive. We are looking at a massive paradigm shift in how machines read. We are moving away from flat, text-based retrieval systems, that lazy undergrad approach, toward fully multimodal, agent-native knowledge orchestration.
Right. And we explored how their 5-module minor use schema captures the total anatomy of a paper, including the implicit motivations and a 5-level hierarchy of citations.
Yeah, and we looked at the sheer elegance of semantic anchors, which finally allow AI to understand how a complex visual chart relates directly to a text paragraph.
Plus, we saw how a hyper-efficient 4B extraction model, trained with strict formatting rewards and GRPO, can process millions of papers cheaply.
And we saw the real-world result. Scholar KG, a 2.46 million paper web of knowledge that dramatically boosts the reasoning power and the rationale accuracy of top-tier AIs. But I want to leave you, the listener, with a final provocative thought to mull over.
Let's hear it.
We've talked a lot today about how this system helps AI read and summarize the science that human beings have already done. But if a system like Agents-K1 can perfectly map out the history, the hidden methodologies, and the subtle citation links across millions of papers processing text, charts, and math as one cohesive, interconnected web.
It ceases to be just a tool for looking backward at our past achievements.
Right. Could a fully orchestrated AI research agent soon start spotting the invisible connections between entirely different scientific disciplines, connections that no human could ever possibly see, simply because no human mind can hold 2 million papers in its head at once?
That's the real frontier.
We might be looking at a system that doesn't just summarize past human discoveries, but actively predicts the next major breakthroughs in physics or biology or materials science that human scientists haven't even conceived of yet.
When you map out the entirety of human knowledge with that level of rigorous precision, the blank spaces on the map, the places where the next big discoveries are hiding, become very, very obvious.
The next time you ask an AI to research a topic for you and it gives you that confident, beautifully written, but ultimately shallow summary, just remember, the days of the lazy, regurgitating AI are numbered. We are finally building systems that don't just read the words, they deeply understand the evidence. And that changes absolutely everything. Thanks for joining us on this deep dive.